In this video, we're going to look at chemical naming. So to start off with, as we saw in our last lesson, a very quick recap. An ion is formed when an element gains or loses electrons to become positive, which is a cation, or negative, which is an anion. In chemistry, compounds that form from the bonding, which we're going to cover later, will become either positive or negative depending on the structure that they have. This then influences the name that we give that compound, and that's what we're talking about today. So let's look at polyatomic ions. So this is an ion that contains more than one atom. So poly, as in poly meaning more than one, some number of, when we talk about like polygons. Atomic, number of atoms, so more than one atom. These don't tend to break apart during chemical reactions. The charges of them apply to the total of the atoms in the formula. So what I mean by that is something like copper 1 nitrate is a copper which would form a plus, so Cu+, and I have a nitrate. We're going to look at what a nitrate is if we haven't already a little bit later, NO3-. So we've got a plus and a minus. So they're going to neutralize each other. The total thing, copper nitrate, has no charge, but the individual atoms do. So this would be copper, NO3 is nitrate, so copper nitrate. Here's a list of some common polyatomic ions. So in chemistry it can be really helpful because once you know all these conventions of how do we name things, it actually makes it really easy to try and come up with a name of something you've never even seen before. So we said before, NO3 is a nitrate. There are other versions, like a nitrite is NO2. Sulfate is SO4, and we've got things like hydroxides we looked at last time, the OH-. What else have we seen? Carbonate we've seen, CO3 2-, like sodium carbonate. Sulfate, we've got it here. So lots of different names. So as soon as we identify like an SO4, we can go, oh, that's a sulfate. An NO3, that's a nitrate. We can start to sort of identify combinations. So if these are sort of the second part, as we've seen with carbonate, there's always something in front. So we can have a sodium carbonate, an NaCO3. We can have a magnesium carbonate, an MgCO3. So we can use these rules to try and identify what a thing is called. So let's look at some of the rules. The positive ion is named as the metal with the word ion added to it. For example, a sodium ion, a magnesium ion. That's how we name it. So it's the metal with the word ion added to it. A negative ion is named with the ending of the element's name removed and swapped for an "ide." So things like nitride, fluoride. If you look back at our table, you see the ides. Where have we got an ide? Cyanide is a negative. Peroxide is a negative. So this links with what we were talking about here, that the negative ions are named with the ide term. So if we have a negative, it's an ide. If we've got a positive ion, we name the metal with just the word ion after it. So if it's just like sodium ion, magnesium ion, if it's got the negative, it's an ide. So how do we know what kind of compound we have? For example, acids often begin with H in their formula. Some of the examples that we're going to see, particularly in our course, some really common ones are HCl, which is hydrochloric acid. So hydrogen chlorine, so you get that hydrochloric. Nitric, so NO3, remember, that created our nitrate. But in this case, because it's an acid, we've got an H in front that tells us it's an acid. We just use sort of that nitra sound, so it's nitric acid, so HNO3. Sulfuric acid, again, it's got an H in front and it's got this sulfate effect, but we use the S, the sulfur, so it's sulfuric acid. Phosphoric, same principle, it's named after the P, the phosphorus, it's got an H in front that tells us it's an acid. So we're looking for H's in the front of the chemical equations to identify acids. For bases, they often have metal hydroxides. So some of the examples we're going to see are sodium hydroxide. So what we mean by a metal hydroxide is the OH. That's a hydroxide if you remember back to what we talked about with bases. OH is hydroxide. Sodium is a metal. If you look back on the periodic table, it's counted as a metal. So we've got a metal and a hydroxide. It's sodium hydroxide. We've got KOH, potassium hydroxide. We've got magnesium hydroxide. So again, the equation's a little bit different, but it's a magnesium and it's an OH, a hydroxide. And we can also have things like calcium hydroxide, CaOH. And in this case, just as a side note, the 2's, those subscripts, are referring to the entire bracket. So we've got 2 of everything in the bracket rather than a big number, which would give us 2 Ca's. We don't want that. It's just a little bit nicer than writing O2H2. So often we'll put it in brackets and write 2 of that. What about carbonates? Carbonates contain a CO3 in their formula. So CO3 is carbonate. Examples we'll see are sodium bicarbonate. So don't worry too much about the bi part. That's not super obvious. We've got a carbonate, we've got a sodium. So it might look something like sodium carbonate. It's pretty close, but it's actually sodium bicarbonate. Sodium carbonate is a little bit different, but very similar. It's Na2CO3. So that's sort of the tricky distinguish to how do I identify sodium carbonate versus sodium bicarbonate. And this is the more common. This is your baking soda one. So the next thing we'll look at is state symbols. This tells us physically what state the chemical is in. So when in a reaction, in a chemical reaction, objects, compounds, materials, reactants can change states. So we use this notation. We use S for solid, seems pretty straightforward. L for liquid, G for gas. AQ means aqueous. Aqueous means it's a solution in water, as in it's mixed with water. Acid and base solutions are always aqueous. They always contain water. It's pretty much impossible to get just a pure acid with no water in it because it requires almost a water solution. And as we talked about previously, if we want to dilute the acid or dilute the base, we add water. So we're going to have this aqueous component. So an example, sodium hydroxide is reacted with a solution of hydrochloric acid to give a solution of sodium chloride in water. We're going to have NaOH, so remember sodium hydroxide. The S tells us that it's a solid. So this is a powder. HCl, hydrochloric acid, is aqueous. It forms sodium chloride, aqueous. So remember sodium chloride is really salt, but this salt is mixed with the water. So it's salty water. Plus it also has H2O, water in liquid form. So that's what we mean by those state symbols. You don't see them very often, but if you do, sometimes in more complex equations, you're going to see the little state symbols. You really only do it if you have different states or the states are changing and you want to know what they are. Some of the other conventions. Chemicals, molecules can be identified by the number of each element using scientific or Latin words. So for example, we see the word mono, which means 1. Di, Di means 2. Tri means 3. Hexa means 6, etc. So using some of these conventions, see if you can come up with what the following are called. So we would start by naming it, in this case, by the first component. So S is sulfur. Now, we wouldn't say like fluoride hexa. We say the number of it first. So it's like sulfur 6-fluorine, which would be sulfur hexafluoride. So if you said hexafluorine, you're pretty close. It's sulfur hexafluoride. Something like this. This is the one we already know. Carbon, 2 of them, dioxide. So that's why it's dioxide. It's not carbon oxide or carbon oxygen. It's carbon dioxide. And this one, again, remember mono means 1. So CO is carbon monoxide. So that concludes the lesson on the naming conventions. Hopefully that expands your understanding of some of these chemical equations that we might have seen so far. And as we go through the rest of this course, you're going to have a greater appreciation of the equations, what states they're in, and how you would actually name the products that are produced. I'll see you next time.